Billions of tons of volcanic rock are sliding into the Mediterranean Sea right now. Not over centuries, not in some distant future, but measurably, trackably, every single day. Mount Etna's southeastern flank is moving as one massive block several cubic kilometers in volume. And every GPS station, every satellite pass, every seismic monitor is screaming the same thing. It's accelerating. The fractures opening across the mountainside, the earthquake swarms concentrated along specific fault lines, the deformation patterns spreading from the summit to the seafloor. All of it matches exactly what happened 8,000 years ago, when the last catastrophic collapse sent a tsunami across the entire Mediterranean that wiped out coastlines from Sicily to North Africa. Over 1 million people live directly on the path right now. When this flank gives way, and scientists are clear that it's when, not if, the resulting waves could exceed 100 feet with less than 5 minutes of warning for Catania, a city of 300,000 people. 5 minutes. That's not enough time to understand what's happening, let alone evacuate. The most recent analysis of ancient tsunami deposits tells a story that volcanologists are struggling to communicate to the public without causing mass hysteria. The last time Etna's flank collapsed into the sea, it generated waves that traveled over 1,000 miles, wiping out settlements from Sicily to North Africa and fundamentally reshaping Mediterranean coastlines. That event happened when the region's population was minimal, scattered agricultural communities that left barely any archaeological trace. Today, the city of Catania alone has over 300,000 residents living within direct striking distance. And that's just one city among dozens of densely populated coastal zones that would be hit within the first 2 hours. Mount Etna towers 3,357 meters above Sicily's eastern coast, though that height shifts constantly as eruptions build the summit higher while gravitational collapse tears sections away. This is Europe's tallest and most active volcano, but it wasn't born on stable ground. The African tectonic plate is diving beneath the Eurasian plate directly under Sicily in a continental collision that began millions of years ago and continues with relentless force today. As the descending African plate melted deep within the Earth's mantle, superheated magma forced its way upward through fractures in the crust, building layer upon layer until Mount Etna emerged as one of the planet's most powerful volcanic systems. But those same forces that created this geological giant are now tearing it apart from within. Unlike stable volcanoes rooted in solid bedrock, Mount Etna's foundations rest on fractured, unstable ground that includes ancient marine sediments from when this region lay beneath the sea. The volcano's steep eastern flank sits directly atop the Alto Etna fault system, a network of massive offshore fractures running beneath the Ionian Sea that acts like a conveyor belt, slowly dragging sections of the mountain toward the ocean depths below. Etna's growth pattern has been catastrophically uneven, with its eastern slopes swelling over centuries as lava flows pile higher and magma intrusions inflate the mountain's interior. These magma chambers expand and contract with each eruptive cycle, creating internal pressures that fracture the rock from within. The combined assault of gravity, tectonic movement, and internal magma pressure has pushed Mount Etna into an unstoppable drift toward the sea. The volcano keeps building itself higher through eruptions, even as its massive eastern flank is steadily pulled seaward. And scientists describe this as a volcano caught between two opposing forces, being constructed through ongoing eruptions, even as gravitational collapse tears the entire structure apart. The mountain grows upward while simultaneously sliding toward its own destruction, and the evidence for how this story ends is scattered across the Mediterranean seafloor in debris fields that tell a disturbing tale. Offshore scientific surveys have discovered huge fields of volcanic debris across the seabed, the remnants of submarine collapses that occurred approximately 8,000 years ago when enormous sections of Mount Etna plunged directly into the Ionian Sea. Sediment analysis confirms these collapses were catastrophic and sudden, occurring within minutes rather than over gradual geological timeframes, and the displaced water volume was massive enough to generate tsunamis that devastated coastlines hundreds of miles away. The most striking physical evidence still visible today is the Valle del Bove, a vast horseshoe-shaped depression carved into the volcano's eastern flank that measures 5 kilometers wide and plunges 1 kilometer deep. This enormous scar is the unmistakable signature of a catastrophic landslide, that occurred tens of thousands of years ago when a massive section of the mountain simply gave way. But the pattern didn't stop in prehistory. Mount Etna's eruptive history stretches back over 2,500 years of recorded human observation, with ancient Greek poets and philosophers writing about the volcano's terrifying power. And since 1500 BCE, more than 200 eruptions have been documented. The deadly 1669 eruption buried entire villages and sent molten rock flowing to Catania. Later eruptions in 1928, 1971, 2001 to 2002, and 2021 repeated the same worrying pattern, with fissures opening along the southeastern flank and instruments recording the mountain inching steadily seaward with each volcanic event. Each eruption subtly deforms the mountain's structure, creating new fractures and exploiting existing weaknesses. And scientists now understand that Etna's entire structure is behaving like one vast, slow-moving landslide driven by magma pressure, gravity, and tectonic strain working together. For decades, geologists believed that Mount Etna's flank motion was driven primarily by magma pressure building within the volcano's internal chambers. But that fundamental understanding changed completely between 2016 and 2018. Researchers from the GeoMar Helmholtz Center for Ocean Research and INGV deployed a network of underwater acoustic transponders along Etna's submerged southern flank to measure seafloor motion with unprecedented precision. And what they discovered in May 2017 shattered every assumption about how Mount Etna was collapsing. The underwater instruments recorded a 4-centimeter shift occurring over just 8 days, a movement that happened completely without any volcanic eruption or earthquake to trigger it. This slow slip event revealed something never documented at any volcano on Earth. Mount Etna's entire southeastern flank, including massive sections beneath the Mediterranean, was sliding as one enormous block. The flank was no longer being pushed by magma, it was being pulled by gravity itself, the mountain's colossal weight dragging it toward the ocean floor below. Monitoring showed this gravitational motion often accelerates after major eruptions or earthquakes, demonstrating how fragile the system has become. And satellite data combined with ground-based GPS stations confirm the sliding continues relentlessly today. Between 2021 and 2024, following several powerful eruptions, scientists recorded renewed deformation across the volcano's summit and flanks with high-precision instruments detecting movements measuring millimeters per day that accumulate into meters of displacement over years. Swarms of small earthquakes have rattled the region with disturbing frequency, and the most alarming discovery is that offshore tectonic shifts and surface movements are now occurring in perfect synchronization, suggesting the entire system from seafloor to summit is moving as one interconnected failure mechanism. In 2024, radar studies indicated accelerations along the submerged Alto Etna fault system, the same zone that hosted submarine landslides 8,000 years ago. And researchers warn that although collapse is not imminent, Etna's flank is sliding faster and across a larger area than ever observed before. The process has already begun. Scientists can measure it, they can track it, but they cannot stop it. And then June 2025 arrived with a dramatic escalation that sent renewed explosive eruptions towering hundreds of meters into the sky above the summit craters. Ash columns rose high above Sicily's eastern coast, visible for dozens of kilometers, and forcing temporary airport closures as volcanic debris drifted through commercial flight paths. The intensity shocked even veteran volcanologists who have spent decades monitoring Etna's behavior, because this wasn't just surface activity releasing pressure from shallow magma chambers. This was evidence of deep magma intrusion forcing its way into the volcano's weakest zones. Persistent seismic swarms rattled the region throughout July and August 2025, with monitoring networks recording hundreds of small earthquakes concentrated along the southeastern flank within just weeks. The earthquake pattern wasn't random but showed clear linear progression, suggesting magma was forcing open new pathways through fractured rock already at its breaking point. Each tremor indicated another fracture opening, another weakness exploited, another step closer to catastrophic structural failure. And the timing coincided perfectly with dramatically increased ground deformation measurements recorded by GPS stations positioned across Etna's unstable southeastern slopes. High-precision instruments detected surface movements exceeding anything recorded during previous eruptive cycles, with some monitoring points showing displacement rates that doubled or tripled compared to baseline measurements. The deformation was concentrated precisely in zones geological surveys identified as most vulnerable to collapse, and what the combined data reveals is deeply alarming. Magma is not just erupting from Etna's summit anymore. Magma is intruding laterally into the already weakened southeastern flank, forcing its way between layers of fractured volcanic rock and ancient unstable sediments. Each injection of superheated magma acts like a massive hydraulic jack, adding both heat and pressure to slopes already sliding under their own weight. The magma intrusions are pushing the mountain apart from within, while gravity pulls it downward toward the sea, and scientists describe this as a dangerous feedback loop that accelerates with each eruptive cycle. Eruptions inject fresh magma into the flank, making the slope heavier and more unstable. This instability triggers earthquakes as rock fractures under stress. The earthquakes allow the slope to slide more freely, creating space for additional magma to intrude. The cycle repeats and intensifies with each iteration, bringing the mountain closer to catastrophic failure. Comparison to historical patterns makes the current situation even more terrifying because the activity in 2025 mirrors conditions that preceded major flank movements in 2002, when significant eruptions caused measurable displacement. But current deformation rates don't just match those events, they exceed them by significant margins. Scientists are being forced to recalibrate monitoring thresholds because the mountain is moving faster now than at any point in recorded history. Each eruption, each earthquake, each centimeter of measured displacement brings the moment of catastrophic collapse closer to reality. And if Mount Etna's unstable southeastern flank were to suddenly give way, the catastrophe would unfold with a speed that makes evacuation virtually impossible. In the worst-case scenario that scientists have modeled extensively, billions of tons of volcanic rock would collapse into the Ionian Sea within minutes. The trigger could be a massive earthquake, a major explosive eruption, or the slow gravitational sliding simply reaching a critical threshold where rock can no longer support its own weight. The moment of failure would be instantaneous and irreversible. Upper slopes would fail first in a catastrophic landslide, with rock debris accelerating down the mountainside and hitting the Mediterranean at tremendous velocity, and the impact would displace massive volumes of water instantaneously. A tsunami wave would form within seconds, rising 20 to 30 meters high as the ocean responds to billions of tons of rock suddenly occupying space where water existed moments before. The wave would race towards Sicily's eastern coast at hundreds of kilometers per hour, moving faster than any evacuation could proceed. And the city of Catania, home to more than 300,000 residents, sits directly in the tsunami's path with almost no time to react. Within 5 minutes of initial collapse, walls of water would strike the coastal city before most people could understand what was happening. Coastal neighborhoods would be completely inundated with water surging kilometers inland and overwhelming everything in its path. Buildings would be swept from foundations, infrastructure would collapse, and entire neighborhoods would simply cease to exist with potential casualties reaching hundreds of thousands. But Catania would only be the beginning because the tsunami would spread outward across the entire Mediterranean, losing some energy but remaining devastatingly powerful. Calabria on Italy's southern mainland would be struck within 15 minutes. The island nation of Malta would be hit within 30 minutes with waves overwhelming low-lying coastlines. Greek coastal cities would face impact within 1 to 2 hours, and North African shores would receive destructive waves devastating ports and tourist centers across hundreds of kilometers. Scientists predict the collapse would unfold in multiple terrifying phases, with deeper sections near the coastline following after upper slopes fail and trigger the initial tsunami as structural support disappears. Each successive collapse would intensify the tsunami's power with secondary waves possibly more destructive than the initial impact, and these follow-on collapses could continue for hours, sending wave after wave and preventing any rescue operations. The historical precedent is horrifyingly real because approximately 8,000 years ago, a massive flank collapse at Mount Etna triggered a Mediterranean tsunami that geological evidence shows reached distant coastlines, and that ancient event occurred when population density was minimal. The same process today would impact millions living in densely populated coastal zones. A 5-minute warning is impossible for mass populations to act upon. Emergency services would be overwhelmed, roads would become instant gridlock, and the catastrophe would be over before most people understood it had begun. Given the immense risk facing Sicily and the broader Mediterranean region, Mount Etna has become one of the most intensively studied volcanoes on Earth, with the INGV Catania Observatory operating an extensive network of sophisticated instruments measuring every aspect of the volcano's behavior around the clock. High-precision GPS stations track ground movement across the mountain with millimeter-level accuracy, detecting even the slightest shifts that might indicate accelerating collapse. Gas emission sensors continuously monitor volcanic gases escaping from summit craters and flank vents, providing early warning of magma movement beneath the surface, while seismic networks record every tremor and earthquake, from tiny microquakes to larger events that shake buildings across eastern Sicily. European Space Agency satellites equipped with advanced radar systems pass over Mount Etna multiple times per week, using interferometric techniques to detect terrain shifts measuring just millimeters across vast areas, creating detailed deformation maps showing exactly where the mountain is moving, how fast it's sliding, and whether the process is accelerating. Since the 2018 discovery that Etna's flank is sliding beneath the sea as one enormous block, researchers have dramatically expanded monitoring efforts into the underwater realm, with ocean bottom sensors and tilt meters deployed along the Alto Etna fault system recording movements that link surface deformation to deep structural motion occurring kilometers beneath the Mediterranean seafloor. Despite this unprecedented monitoring effort, predicting a gravitational flank collapse remains extraordinarily difficult because, unlike volcanic eruptions, which often provide clear warning signs days or weeks in advance, gravitational collapses can occur with minimal warning or none at all. A collapse could be triggered suddenly by an earthquake or eruption, or occur spontaneously when accumulated stress exceeds the threshold fractured rock can withstand. Scientists are exploring early warning thresholds based on rapid acceleration patterns in GPS measurements, sudden increases in seismic activity, changes in tremor patterns indicating structural failure, and offshore sensors detecting submarine landslide initiation. But these warning signs might provide hours of advance notice in the best-case scenario. The margin for detection is dangerously narrow, and warning time might be only minutes. The response preparedness gap reveals a brutal reality. Civil protection authorities have plans for volcanic eruptions, but large-scale collapse and tsunami demand a completely different response system that doesn't exist. Evacuating hundreds of thousands of people in 5 minutes is logistically impossible, and while international collaboration has improved tsunami warning capabilities, all findings point to the same conclusion. When Etna's flank collapses, catastrophe will unfold faster than human systems can respond. Mount Etna has always been in motion, a geological reality that defines the volcano's entire existence and shapes eastern Sicily's landscape. Each eruption reshapes the slopes by adding fresh layers of lava and ash while simultaneously weakening internal structure. Each earthquake shifts the mountain's foundation, exploiting existing fractures and creating new pathways for gravitational failure. And through it all, gravity pulls the massive southeastern flank steadily toward the Ionian Sea below in a process that's been continuing for thousands of years with no sign of stopping. The movement is slow by human standards, measuring just centimeters each year in most monitoring locations, but the process is completely irreversible once it reaches the advanced stage where Mount Etna now finds itself. Once massive gravitational sliding begins at this scale, once billions of tons of rock start moving as a coherent block under their own weight, nature offers no mechanism to reverse the process or halt the inevitable progression toward catastrophic collapse. Scientists have warned that a major volcanic eruption could trigger rapid acceleration, transforming current slow drift into sudden failure within hours or days, and a large earthquake rupturing the Alto Etna fault system could destabilize the entire flank instantly, sending the mountain crashing into the Mediterranean without warning. The 2025 volcanic unrest strongly suggests Etna's internal magma pressure is building to dangerous levels not witnessed in decades, creating conditions matching patterns observed before historical flank movements and major structural failures. The timeline uncertainty is perhaps the most psychologically difficult aspect of the threat, because catastrophic failure might still be centuries away, occurring so gradually that dozens of generations will witness the slow-motion disaster, or the mountain structure might gradually adjust to stresses, allowing sliding to continue indefinitely without sudden collapse. But the next major earthquake could also trigger instant failure tomorrow, next month, or next year, giving coastal populations absolutely no realistic opportunity to escape. Over 1 million people currently live in Mount Etna's shadow, with their entire lives built on land that satellites confirm is sliding toward the sea. Catania continues expanding despite the threat, with new construction proceeding as if monitoring data doesn't exist, and Sicily's economy depends heavily on tourism to volcanic landscapes with thousands of visitors annually hiking Etna's slopes, completely unaware they're walking on a slow-motion landslide. Development continues in high-risk coastal zones with valuable beachfront property commanding premium prices, even though it sits directly in projected tsunami inundation zones. The economic reality creates political pressure against sound safety planning because Sicily's fertile volcanic soil supports agricultural operations worth billions annually, tourism generates massive revenue, and relocating populations would be economically catastrophic. Political leaders face intense pressure to downplay risks because honest threat assessment would require politically and economically unacceptable actions. The scientific consensus is absolute. Collapse is inevitable. The debate centers on when, not whether, the Mediterranean will face a major tsunami from Etna's flank collapse. The only unanswered question is whether catastrophe happens in our lifetimes or our grandchildren's lifetimes. And every measurement, every earthquake, every eruption brings that answer closer to being revealed.